Mats Lárson, member of the Nobel Committee for Physics. Two inventions were awarded today. It was about the tools made of light. It sounds actually like science fiction. Can you say something of the history behind the optical tweezers, for example?
Well, I think that Arthur Ashkin, very soon after the first laser had been constructed, realized that suddenly there was available a tool of light of a totally different quality than you had earlier. And he started to think about how can one use this tool to manipulate objects. And he realized that by thinking about this, he realized that just take a small micro-sized transparent sphere should be possible, even if the radiation pressure from the laser is very small. It should be possible to manipulate such a sphere. And indeed he was correct, and already in 1970 he had demonstrated this. So that, but then of course there was a long development, one development that went into the direction of manipulating atoms, something much smaller than micro-sized sphere. But he also started to think about something much more complex than a sphere, namely viruses, bacteria, even living cells he could trap. So that was of course the real breakthrough, that one could manipulate such very complex objects.
At the same time, you can say that the dream of using radiation pressure, yes, for example, like solar rays, is a very old dream of mankind.
Of course, I mean, if you go a long time back, I mean, already Kepler realized that radiation pressure from the sun could explain how the comet tails are behaving when they are coming in and out in the neighborhood of the sun. So indeed it is an old subject, but it was really the invention of the laser that put it into the laboratory. Prior to that, I mean, you didn't have light sources that would work.
But now we have a laser. So would it be possible to use optical tweezers in moving objects in space, for example?
You mean out in space?
Yes, maybe.
I guess so. I haven't thought about that direction really, but in space, I mean, I guess there you want to have, if you want to have more than one spaceship, what you really need is to keep them extremely precise with respect to each other. And there the laser, of course, plays a very important role. And this is a development I think we will see in the next 20 years, for example, in space-based detectors for gravitational waves. And there the laser plays an extremely important role.
And the other part of this year's prize is about high-intensity lasers, very short pulses. Why did they want to develop such thing?
Well, I think there are several reasons. I mean, if you saw the curve I did, there was a sort of a plateau over 15 years. And as a physicist, you always want to go to the new frontiers. You want to push the pulse intensity. You want to go to higher and higher intensity, where you really start to not only talk to the molecule or atom, but really to seriously influence it. And this is something that really started with the invention of the CPA technique, because then you get pulses of sufficiently high intensity so that when interacting with atoms and molecules, it was no longer a small perturbation, but it was a drastic change of the electron shell of the atom. And this then led to strong field physics and attosecond metrology in physics, attosecond science. So that was an important application, rather unexpected, I would say. I mean, around 1985, there was no clear understanding of what would happen if you expose atoms to such strong fields, strong laser pulses.
And now you can take a movie of what's happening in the atom.
Yes, you can start to take movies of the electron motion in the molecule or atom. And this was, of course, science fiction for a long time.
You show the curve in the development of intensity for lasers, and it kind of never stopped. How intense can those laser beams become?
I don't see a showstopper right now. I mean, there will be new materials, there will be new ideas how you can. The basic science is understood, and then it's the question of the scale and how big you can do things and so on. And so I don't see that there is. This will go on, and that's what I indicated with the dashed line. I mean, it's going on for one more decade.
How big are those instruments, optical tweezers or high-intensity
Optical tweezers
lasers?
can be a very small instrument. That's more like a microscope. The CPA-based lasers, I didn't have time to show it here, but it can either be a very compact instrument that you use for eye surgery, which is something that fits easily into a. I mean, it's not more bigger than when you go to the dentist, for example. I mean, it's the same size of instruments. When you come to laser plasma acceleration, then we're talking about really big lasers. I mean, filling up a big laboratory. But that's the beauty of this technique is that it's scalable. It's scalable. You can scale it down if you want to have high rep rate. You want to have ultra precise. Interaction with something, for example the eye, or you want to drill, or you want to make stents and so on. Or you can emphasize really the high intensity frontier. And if you interact the really highest intensity pulses with matter, then of course you're creating extreme conditions that doesn't really exist on Earth naturally, but for example may exist in astrophysics, in the interior of planets and so on. And, so that's direction I would call laboratory astrophysics.
It's extremely intense.
Yeah, extremely intense, precisely. But still with a rather high rep rate. I mean, 1 hertz is quite, it's quite often when you have this high.
Every second.
Yes, every second.
Donna Strickland, one of the laureates this year, is not only the third woman in physics, Nobel Prize history, but also she was a PhD student when she made this invention.
Yeah.
Do you have any good advice for PhD students today how to pick up important issues to work on?
I think if you're a potential PhD student, you should look for something that really interests you. You should look for groups that are very good in that particular area that interests you, and then try to start to get a PhD position in one of these groups. I think if you start with something that doesn't really inspire you, I don't think that's not right. Then you're on the wrong track. You should choose the topic first, then look for people that are doing this, and try to select the best. It's not easy, admittedly, but.
Thank you very much. That's
Okay.
Lárson.
Thank you.